Right, good day, good people. Wow, it's amazing to be here in person, such a great venue with you all. And I have to say, thank you very much for joining us in today's session on scaling foundation model inference with SageMaker. And now, what if I tell you that this whole presentation and the demo that you're going to see in this session is completely used and created by generative AI? Shocking? Well, the reality is we handcrafted this whole presentation and demo, but I wish I could do that. Well, my name is Dhaval Patel. I lead the solution architecture team of machine learning specialist team at AWS. We help customers like Salesforce is joining us today, scale machine learning workloads on AWS. And I've been joined by my colleague Alan Tan, who is from the SageMaker product team for inference. He's going to share new features that we are launching in SageMaker inference today in this session. And then we are very honored to have the vice president with Salesforce, who's responsible for building machine learning platform. And he's going to share his story and how his team uses SageMaker in scaling foundation model inference at scale cost efficiently. His name is Bhavesh Doshi. We are very honored to have you, Bhavesh, here in this session. So a quick question, and feel free to raise your hand if I ask questions. So who all are building generative AI applications currently? All right, almost all. All right, cool. Who are all using open source foundation models for that? Open source foundation model. Quite a lot. All right. How many of you are using SageMaker for deploying the models? All right, cool. All right, how many of you need to use more than one foundation model for inference, for building applications? More than one. Cool. All right, we got good audience. You're going to love it. All right, let's get started. So we are seeing a paradigm shift today as the organizations are strategically embedding generative AI applications in their very fabric of daily operations. And the result is unlocking new possibilities, unleashing the new unprecedented level of productivity increase. And the core foundation to building the generative AI applications is foundation model. A foundation model is a large, pre-trained, transformer-based model that is best in either generic tasks or fine-tuned towards like doing this specific task. And generally, there's more than one foundation model involved in building an end-to-end generative AI application for the production use. Now, let me give an example for that. A generative AI chatbot application needs a variety of different foundation models, including toxicity detection, PII detection, summarization, Q&A models, workflow generation, search models, embedding models. The list goes on and on and on and on. Now, on top of that, customers are also wanting to improve the accuracy of these foundation models that they're building based on their customer data sets or domain data sets. And they want to fine-tune these foundation models further and deploy them in the production. On top of that, you want to use multimodality of the data like image or text or code or video. And the list goes on, and you quickly end up having multiple foundation models, maybe from tens to 50s, to even hundreds of foundation models that you end up deploying at scale. And you need a scalable way, cost efficiently, to host these foundation models at scale. So additionally, these models are large number of hundreds of billions of parameters, hundreds of gigabytes of memory that's needed to load these foundation models. And they are based on transformers architecture, and transformers are slow. And it could get surprisingly slow even on the expensive hardware. Now, think about the lot of iterative experimentation that you have to go through in performance, tuning these foundation models in order to get the best response time and throughput at low cost. And don't forget, you have to also put the guardrails on making sure that you isolate these models take care of the area of impact. You control the area of impact, put guardrails so that one model does not end up having a problem with the other models, and you prevent the noisy neighbor problems. And by the way, you might end up having hundreds of inference endpoints to host these foundation models. It's going to increase the operational overhead for you. So how about I take your journey of deploying a single model, single foundation model into production, and let's see how you can scale to hundreds of foundation models at scale, cost efficiently, using SageMaker. Let's get started. So the first thing that you do in order to host a foundation model is calculate its size. Now, the size of the model, here in this case, we take an example of Llama 2 13 billion model. The size of the model is primarily dependent on the number of parameters and the size for each parameter. Now, Llama 2 13 billion is a 13 billion parameter. So you have 13 billion parameters, and each parameter taking 4 bytes, which is FP32, we get about 52 gigabytes of memory just to load the parameters of the model. Now, in a large language model, foundation model, there's an autoregressive decoding process that takes the input tokens and processes these tokens iteratively to output the next token. And during this whole process, it ends up creating attention key value tensors that it has to keep into the memory. And that also occupies an additional 4 to 10 gigabytes of memory. In addition to that, you need to use frameworks like PyTorch or NVIDIA CUDA. Additionally, are going to occupy about 3 to 4 gigabytes of memory. So overall, we're talking about 65 gigabytes of memory just to load up one instance of Llama 2 13 billion. Now, you can always try to optimize this by compressing the size of the model by using different techniques like quantization mechanism, but that comes with a trade-off with the accuracy loss. So for now, we are going to keep on using 4 bytes per parameter, so we still have 65 gigabytes of model to handle, just for the one instance. All right, so we have 65 gigabytes of memory to load, and we choose an instance. Here in this case, we choose an ML instance P4D, which has 8 NVIDIA A100 GPUs. Each GPU comes with 40 gigabytes of high bandwidth memory. So obviously, we cannot fit 65 gigabytes of model into any of the GPU's memory. So we split that model by using model partitioning logic or model parallel logic. And we split the whole model into 2 shards. And we occupy 2 GPUs out of 8. All right, well, what about the rest of the 6 GPUs? They are just sitting idle out there. So we still have 75% compute and memory free and idle. And so can we make it more efficient? Let's see how. So how about we load additional copies of the same model, load them up into the rest of the 3 GPUs so that we saturate and we maximize the utilization of the memory. So we load these models up in the additional GPUs, we get ultimately 4 model copies. And then possibly we can drive up the utilization of the GPUs to its 100%. Now that depends on if the model receives enough production traffic to drive up the utilization of the compute to 100%. If the model is not being invoked as much as we expect, then it's going to sit idle, and you're not going to have the best price performance. All right, so let's keep that in mind. So let's put this model into production and scale according to the traffic of the model. So for that, SageMaker Inference offers the broadest and deepest set of inference options for any use case that you can use. And you can use a fully managed SageMaker real-time inference endpoint and invoke this endpoint using a RESTful API and get the streaming response. SageMaker also supports offline inference options for large data sets. And if your payload is large in size like image or video, you can also use SageMaker asynchronous inference endpoint and scale down to 0 depending on the traffic. Now you can also host one model, or you can also host ensemble of models. You can also orchestrate these models into a serial inference pipeline, put them together, orchestrate the workflow in the SageMaker endpoint. You can also host multiple models into the same endpoint as well. On the hardware side, infrastructure side, you can use CPUs, AWS Inferentia, NVIDIA GPUs, or go even completely serverless. All right, so let's use SageMaker's real-time inference endpoint to host Llama 2 13 billion model for our chatbot use case. All right, so you have Llama 2, and then you have a container that you have to choose to host this model. In this case, we're going to use large model inference container. Now, do use this container because we just launched slew of new features of large model inference container in SageMaker, which will give you 20% lower latency on average. With these new features, we introduced new optimizations like optimized all reduce algorithm. We also have integration with the TensorRT LLM backend as well. That will give you optimized performance in terms of response time and throughput. So do use large model inference container for hosting foundation models on inference. All right, so we have large model inference container, and we pick a machine learning instance. Here in this case, we use P4D as I presented before, which has 8 GPUs. All right, now we attach an auto-scaling policy to scale horizontally based on the user traffic. So you attach that on the SageMaker inference endpoint and scale horizontally to n number of instances depending on the throughput or depending on the hardware utilization or depending on the response time targets. And then user can invoke that using a RESTful API and get the streaming response. All right, sounds good. So you have a Llama 2 model up and running in production, scaling out for your chatbot. Cool. All right, now you want to moderate the content of your chatbot application. So you now have toxicity detection endpoint. Oh, by the way, you also want to protect the PII data of your customers, so you also have PII endpoint. Cool. By the way, you just forgot that your chatbot does not hallucinate. So you decide to add search model and embedding models, and then you also want to support additional use cases for developer, wherein developer can also use your chatbot for the code generation. So you end up having a code generation endpoint. And then, by the way, you need multilinguality. You need speed generation. Oh, by the way, I want to now fine-tune these models based on my customer data. And then you just keep on increasing the number of endpoints. Look at the number of endpoints that you end up hosting and managing this. This is high operational overhead. You can't continue like that. You can't scale like this. You need a better way to cost efficiently serve these foundation models and build generative AI applications on SageMaker. All right, so can we pack more models on the same SageMaker inference endpoint? All right, let's see how. So how about we take these foundation models and host in the single SageMaker endpoint. Now, that's a good option, but if these models do not fit on the machine learning accelerators on that instance, will not be able to fit in, and you'll not be able to host all of the models at the same time. So what do we do here? So, well, then you decide to use SageMaker's multi-model inference endpoint. A SageMaker multi-model inference endpoint gives you a fully managed option to co-host multiple foundation models and spread across multiple ML instances in the fleet. And it loads these models dynamically based on which model is being invoked by the user, and dynamically loads up during the invocation. Now, it also has smart routing logic to route these traffic of inference for that specific model to only those instances that have already loaded them into the memory to avoid the cold start. And it also uses replication based on the popularity of the models. If a model is receiving high traffic, it's going to spin up more replicas dynamically. How cool is that? Great. All right. But however, the initial invocation requests coming to these models are going to experience cold start latency. Because these models are large, they're going to take probably seconds to minutes to load them up onto the high bandwidth memory, and this might not be a good solution for those applications that are ultra low latency sensitive applications. So what do we do here? Well, overall, what you need is for ultra low latency applications, for hosting multiple foundation models at scale for inference, what you need is be able to pack multiple foundation models into a single endpoint to avoid high operational overhead and save cost. And then you also want to make sure that you don't have to deal with the cold start latency. You can load up this memory early before the inference request comes and pin them into the memory. And then you also want to make sure that you have a fine-tuned granular allocation of these machine learning accelerators based on the model's needs. And then you want to also put guardrails to make sure that you provide a fine-grained autoscaling policy based on the model, not just based on the machine learning instance. You should be able to scale out based on the model so that the model who is receiving high traffic can scale versus the model who is receiving almost no traffic. You don't need to scale, and you can scale down to 0 to save cost. So, and then on top of that, you need model-specific metrics for observability, like model-specific response times, model-specific throughput, model-specific hardware utilization. And in order to satisfy these needs, I'm happy to announce the launch of new SageMaker inference, endpoint inference components to satisfy these requirements, and other slew of other performance-enhancing features in SageMaker in this session. And with that, I will hand it over to Alan Ten to dive deep into these new features. Thank you very much.
Very good. Oh, sorry. Okay, who's excited to learn about these new features? Okay, we got a lot of people, so great. Thank you, Nawal, for introducing the background and the challenges that our customers are seeing. First, we added the flexibility for customers to deploy 1 to hundreds of models efficiently by packing them onto a single endpoint. And this flexibility means you can actually grow the endpoint as your use cases change. By deploying multiple models on a single endpoint, we've seen customers save and reduce their inference costs by 50% on average. Each of the models that are deployed on the endpoint can have its own auto-scaling policy, so you can scale them independently. And we've published a new set of CloudWatch metrics and CloudWatch logs to provide you the data to set up very effective auto-scaling policies as well. And not only that, you can scale each of the models that are deployed on the endpoint all the way down to 0, so you can free up hardware for other models to be loaded. You can also dedicate specific hardware resources to different models. So you can say model A gets 2 GPUs, model B gets 1 GPU on the instance. And SageMaker will use this information to efficiently pack your models on the instances for high utilization and availability. We've also launched a new smart routing algorithm that routes requests to instances and copies of the model that are more readily available to serve that traffic. This leads to a 20% lower latency on average. You can use these features with any SageMaker-compatible container. This could be a container that AWS publishes or one that you've built yourself. You just need to make sure it responds to 2 SageMaker APIs, one for health checks and one for responding to the inference requests, of course. Let's take a look at how the SageMaker entities have evolved with this new release. So first, we have the endpoint. This is just an abstraction of the infrastructure and the model that you have set up. You can make HTTP requests to this endpoint to get inference back. And behind endpoint are a set of ML instances that SageMaker manages on your behalf to do things like patching, health checks, and instance replacement in case there are any issues. To enable these features, we added a new SageMaker object called inference components. You can think of an inference component as an abstraction for a model that's deployed and is ready to serve traffic. There are 5 main components of an inference component. The first is the location of your container. This container has your model server, has your inference logic, and it knows what to do with your model weights. And then we need the location of your model weights in an S3 bucket that you own, of course. And you can also specify how many CPU cores, GPUs, or neuron devices, if you're using our Inferentia or Trainium instances, and how much CPU memory this model needs to run. You can also specify how many copies of this model you want to start with to do things like the model pinning that Dawal mentioned earlier. An inference component is also a unit of scaling. So you can set up auto-scaling policies for each inference component. They can be very different between each other. And you can have one or more inference components on an endpoint. And SageMaker will handle placement of those inference components on the instances. And I'll show a deep dive of what that looks like in the next couple of slides. To deploy inference component is very easy, 3 simple steps. First, you pick the instance you want to use by creating an endpoint config. Second, you just create the endpoint, which gives you access to that instance. Third, you create the inference component, which effectively deploys that model onto the endpoint, and you can serve traffic for that model now. We've also released a full set of lifecycle management APIs for you to manage what models are deployed. So you can add new models so they're deployed. You can remove existing models. You can also update them if you have a new version, for example. Let's take a look at a deeper dive into what the auto-scaling and placement logic looks like and how we maximize utilization to help you save costs. Let's take, for example, we have let's say a comic book ML application. It generates the images for your comic book, and it also helps you write the story and the dialogue for that comic book. For this application, we'll use 2 models, a stable diffusion model. This one uses one A10G GPU. This is the GPU on a G5 instance. And we're going to configure it to scale from 1 copy to 4 copies, depending on the number of requests or traffic going to that model. We're going to deploy this on a single endpoint using an instance with 4 GPUs, for example, a G5 12 extra large instance. And because we've said the minimum copy is 1, SageMaker has put 1 copy on one of the GPUs there. Next, we also have a stable diffusion, I have a Llama 2 13 billion model. And this one is quantized, so it can fit on a smaller GPU here. But it still needs 2 A10G GPUs, but is otherwise configured exactly the same. And in this case, we can see SageMaker has placed the Llama 2 13 billion model on the same instance as the stable diffusion model. I've also popped up an auto-scaling monitor, so we can see what happens when the traffic changes and the scaling behavior changes. Let's say a lot of my customers using the app start writing their story and start generating the narrative first. So we see an increase in traffic for the Llama 2 model. So in this case, SageMaker sees that we only have 1 GPU free on this instance. So we'll actually spin up a second instance to get access to more GPUs. And then SageMaker would place enough copies to meet the traffic on that second instance. And then let's say we're done writing, and more people start generating the panels and graphics and art for their comic book. Now, we're seeing more traffic for Stable Diffusion, so SageMaker will spin up another copy of Stable Diffusion, and it will do that using the remaining free slot to maximize utilization. So SageMaker will scale up instances when it needs to meet the inference component scaling policy needs, and it will also try to fill up free slots whenever possible. SageMaker will do the exact same thing even when you have a model that scales down and you have new hardware slots that are freed up. So for example, let's say people stop writing their stories and Llama 2 traffic comes down. So SageMaker will scale down the Llama 2 model. This frees up 2 GPU slots on an existing instance, right? And then let's say more and more people continue generating more graphics for the comic book, and then SageMaker scales up to take those remaining slots as well. So we'll reuse slots before creating new instances to help you optimize for cost. Now, there's actually another optimization we could do, and this is a sneak peek for something we're working on and is coming soon. Let's take, for example, that maybe it's midnight, maybe it's 3 a.m. No one is generating any graphics for their comic book. So because there's no traffic, we can actually scale down the Stable Diffusion model all the way to 0. And now you can see we have 2 instances that are basically 50% utilized. SageMaker will detect this and combine them into 1 to optimize for cost. So instead of paying for 2 50% utilized instances, you're just paying for 1. By default, SageMaker routes requests by random. This has worked really well for classical ML models, where the model latency is short, and you get relatively consistent latency between requests. However, with foundation models, the inference latency can vary from seconds to minutes, depending on the input that's going into that request. And even between requests, we see a very large variation. So what happens with random routing is that even by chance, you can get a short-running request that gets stuck behind 2 longer-running requests. This leads to a longer end-to-end latency for your clients. So what we did was we introduced a new routing algorithm called least outstanding requests. This one, we will route requests to instances and copies of the model that are ready to serve traffic. This leads to a much more even distribution of the requests. As you can see, the short-running requests are processed much faster now. This gives you a much better end-to-end latency. Earlier this year, we also launched a new feature for streaming back responses. So you can create real-time applications that send responses back, such as tokens or chatbots. And then if you're building, let's say, a video generation application, you can stream back the video frames in real time as well. This feature is also compatible with the new launches that I just talked about. So you can stream back responses from each model that's in the endpoint. And we've launched new granular CloudWatch metrics and CloudWatch logs to help you debug and monitor more effectively. So for CloudWatch metrics, we've added new hardware utilization metrics that you can monitor at the per model or inference component level. We've added reservation efficiency metrics, so you can see how many of the reserved hardware is being used. And also, we've broken down the invocation metrics, so you can see how many requests are going to each of your model, and how many of those are failing, how many of those are succeeding. And similarly, we've broken out the CloudWatch logs as well. So you can get logs specific for your inference components and models. So in this case, you can see the Llama 2 inference component couldn't start because it couldn't find a library, so you can easily go and debug that and then just update the inference component afterwards. All of the features I talked about is supported in our SageMaker Python SDK, our SageMaker Studio UI, which I will do a demo of shortly, and is also available through our standard AWS SDK and AWS CLI tooling as well. And of course, to support your infrastructure as code, all of this capability is available in our AWS CloudFormation as well. So let's take a look at a demo of these new features through our interactive UI. So what you're seeing here is a screen of the SageMaker Studio UI. This is the new UI, so it may look a little bit different if you haven't seen it. Let's take, for example, we have a new ML application that generates code using a code gen model, and also a chatbot that teaches you how to use that product and troubleshoots. We want to combine both of these models onto a single endpoint to help us save costs. So because I've already deployed these endpoints and my application is working, we can take a look at the models that are powering this application. And to do that, we will go to the model section here. It will list all the deployed models. Oh, there we go. Just a little delay. So you can see we're going to the model section, and we can see at the top there are two tabs, registered models and deployable models. Deployable models are models that I have previously deployed. So if I click on it, I get a list of models that's been deployed. And because it's an existing application, I can just search for the models that I've used before. So in this case, I created this app a few days ago, so I can search for that date. And here, you can see a list of models now. So for this demo, we'll use the first two models because they're just newer versions. So we'll multi-select the two models, the CodeGen model and the Llama 2 model. And I can create new models here if I want, but in this case, I'll just deploy these. So I'll click Deploy. And now I was pre-generated an endpoint name, but I'll edit it so it's more specific, and I can more easily find it later. So I'll just type in a demo endpoint name here. And I'll also select a P4D instance for high performance, and there's also the instance I'm already using today. And I will also leave the instance count as 1 and have SageMaker scale that up as needed. Both of these models fit on a single GPU, so I'll leave the number of GPUs to be 1. I'll also leave the number of copies to be 1 and have SageMaker scale that up as needed. Both of these models are also GPU bound, so I'll just leave the CPU memory alone as well. If I want to add a new model, I can, but in this case, I just stick with these two. I'll click Deploy. Now we can see some successful notifications of the endpoint being created and the models being deployed. We'll actually skip forward in time because this will take a few minutes. So now we'll come back and we can see that the endpoint is now in service. And also the two models that we deployed are also in service. We can also test these models out directly from this UI to make sure that it is at least functioning as expected. So here we'll click on Test Inference. And we'll scroll down a little bit just to see more of this section. There's a model dropdown here that lets us switch between the two models. We'll try the Llama 2 model first. We'll paste in a sample input here and hit Send Request at the bottom, which was a little bit cut off, unfortunately. Well, we can see the request came back. It looks good. I'll try the same thing with the CodeGen model. So the CodeGen model generates code. So I'm going to paste in a hello world function for it to generate and complete. We'll hit Send Request again. And we can see a hello world function came back. So both of these look good. So let's go ahead and set up an auto-scaling policy for both of these models. We'll hit refresh just to get the models loaded. So we'll go ahead and set up the Llama 2 model first. So we can click on Edit Autoscaling on the right. Here, it's asking me for two properties at the top, scale in and scale out cooldown. This is just to say how long we want to wait before triggering another event. So I'll just leave as these. This is the default, looks reasonable. The instance count range is how many copies of this model I want to scale between. So I'll just leave this as well for this demo. And the target metric is what metric I'm going to scale on. So this is number of requests going to each copy of this model. We'll also put a value of 1 just so we can easily trigger that using this demo. And we just need to select now a role ARN that has permissions to auto-scale. We'll do a very similar thing for the CodeGen 2.5 model. So we'll hit Edit Auto-Scaling again, and just leave all the default values. We will change the invocations to 2, just so we can differentiate it a bit, so you can see that they are actually different scaling policies. So you can see now we have 2 auto-scaling policies. Behind the scenes, this is actually implemented using application auto-scaling, which also creates an alarm in CloudWatch metric that you can use to monitor when the auto-scaling happens, and also monitor the number of requests going to those models. So in the background here, I'm also going to send some fake requests, and we can actually monitor the CloudWatch metrics using the AWS console. So we'll switch to the AWS console very quickly. And here we'll click CloudWatch. Now on the left here, we'll click all alarms just to see all the alarms we have. You can see we've actually created 2 alarms per inference component, one for scaling up and one for scaling down. Let's fast forward to a time when these alarms are triggered, and it's actually going to scale up. We'll take a look at the Llama 2 model in this case, just to see what that looks like. So you can see now these models are in alarm. We're going to look at the Llama 2 model. Because it's an alarm, it actually means the auto-scaling policy has kicked in, and we're scaling up. So you can see this is because in the last 5 minutes or so, we've had more requests than 1 going in. And this CloudWatch is saying, hey, it's an alarm. So we can actually switch back to the SageMaker Studio, go to the Model tab, and confirm that it's scaled up. So you can see for the Llama 2 model, it's now at 5 copies. So it went from 1 to 5 based on the traffic we were sending it. Let's take a look at what the scaling down looks like as well. So we can go to the second alarm here, which is for scaling down. And similarly, we can click on it to get more details, but it's going to scale down when it's less than 1, because that's what we set. You can see that the traffic is already petering out. So let's hit refresh and fast forward to a time a few hours later when it definitely should have scaled down. So we can see now this alarm is also in alarm, which means the model should have scaled down. So we can confirm that again by going into SageMaker Studio. We can see now the number of copies is now back to 1. So we saw it go from 1 copy to 5 copy and back down to 1. So with this, I conclude my demo, and I'll hand it over to Bhavesh to talk about how Salesforce is using SageMaker to effectively host foundation models with high performance and low cost.
Thank you, Alan, so much for the introduction. Hi, I'm Bhavesh. I'd like to share about how Salesforce Einstein 1 platform and the innovations we've made with the AWS team in generative AI, specifically for scaling up inferences for the foundation models. But first, I'd like to thank you all for attending this session. I'd also like to thank the AWS SageMaker team for partnering with us in this journey of providing a trusted AI platform for our customers. And I'd like to thank my teams in Salesforce, in the Bay Area, in Seattle, in Israel, and India. It is their hard work that I am privileged to showcase over here. So with that, let's get into it. So I'm assuming all of you are familiar with Salesforce or are Salesforce customers. Yeah? Great. So Salesforce mission since 1999 has been to help our customers connect with their customers in a whole new way. And that's the premise of the customer relationship management software suites. And as you all know, Salesforce is the #1 CRM by market share by far. So for us, it all starts with Customer 360. Salesforce helps deliver a single source of truth with a 360-degree view of all the customers' interactions. This is the big power that Salesforce brings into the play. So as companies turn to AI to improve their productivity or deliver some awesome customer experiences, they face a key challenge. Most companies can't leverage their data for such experiences because their data is spread across disconnected islands. And as we all know, that when data isn't connected correctly, no amount of AI or automation or personalization will work. So that's where we created the Einstein 1 platform. It is one platform that connects all of your customer data across all of your customer experiences and enables building AI applications and experiences. Let's dive deep a little bit more into the platform. So we built this Einstein 1 platform to deliver an integrated, intelligent, automated, easy to customize, and an open platform for trusted AI. All of our core CRM applications like sales, service, marketing, commerce, as well as data cloud are integrated and native to this platform. And with a new metadata framework, instead of having islands of disconnected data, data is accessible from one platform, even data outside of our CRM. Now, all of your applications will speak the same language, and it gives you a comprehensive single source of truth for each of your customers. It brings native AI with Einstein, built not just for predictive, but also for generative use cases. It's deeply integrated with Data Cloud. It gives you a comprehensive data lake with real-time data access. Very useful for the generative AI use cases. You can access it from your favorite applications like Slack, Tableau, and Heroku, or from any other popular applications or productivity suites. It's easy to customize with the low-code and the no-code options so that you get the benefit of the full platform. And you can build your own applications that are similarly integrated, automated, intelligent, thanks to our open ecosystem, or bring in any integration you want with MuleSoft. So that's the Einstein 1 platform. With the platform, we are also bringing in generative AI use cases to every cloud in the flow of work. This addresses some key operational pain points and opportunities. So for example, Sales GPT automates prospecting of emails so that sellers can spend more time with their customers. Service GPT automates service responses, summarizations of cases, and knowledge articles. Marketing focuses on segment generation, campaign creation. Commerce GPT, it focuses on the dynamic product descriptions, or a concierge service for personalized product discovery. Similarly, Developer GPT uses natural language to create code, chat-based assistance, and auto-completion for coding. All of these Einstein GPT applications use generative AI in every cloud in their workflow. Right? So we are bringing AI where it drives the most impact to your business and focused on unlocking value. So let's look at one example of this. So this is one of the case services. And like on the right side of the screen, you see the Copilot experience, where you can, in natural language, ask something. In this case, summarize the case, and it gives you a complete summary of the case that is helpful for you to figure out what the next action should be. Okay? So now let's look at the trust layer and the architecture of the Einstein 1 platform. So it's delivered on our Hyperforce public cloud infrastructure, which enables us to securely deploy and scale all of the data and AI services while meeting compliance requirements. We have an open model ecosystem. It provides secure access to foundational models hosted outside of Salesforce via APIs, or you can bring in your own foundation models so that you can reuse your generative AI investments and run those models in your infrastructure. We also provide the ability to host foundation models for you if you want a private model. You can also fine-tune some of these foundation models and run on a per-tenant basis in Hyperforce instead of in your own VPC. This is where we've partnered a lot with the SageMaker team on making sure we can scale up inferences for hundreds of foundation models. And because trust is the #1 priority for Salesforce, we've created this Einstein trust layer, which provides you with security guardrails that enable you to ground these AI models using data in your own CRM, but do so with controls like zero data retention that protect data security and privacy. We also use data masking so that these models will never see private PII data, and we ensure better outputs through toxicity detection and through audit trails. So AI at Salesforce is customizable through these low-code builders, such as our new Einstein Copilot Studio, which is the configuration layer for the new Einstein Copilot that I just demoed. And it also enables you to ask questions, not get answers, but to take actions, saving time. So what have we been working with the SageMaker team? So our relationship with SageMaker goes beyond these generative AI use cases. We've been partnering with them for many predictive and generative use cases, and also for multi-tenant inferencing and training. We've worked with Salesforce, with SageMaker on making the data available in Data Cloud. The data in Data Cloud available in SageMaker with zero data copy. We've been working on optimizing model inferences in the large model inference container with innovations such as faster transformer, dynamic batching, and very much interesting things. So these are some of the foundational models that we have developed in Salesforce or we're using via SageMaker Jumpstart right now. And for this example, I'm just going to focus on two of them. The CodeGen 16 billion model, which requires about 75 GB of GPU memory, and currently has a high traffic incoming. And the TextGen 13 billion models, it's a relatively newer model, requires 55 GB of GPU memory, and currently we're seeing low traffic, but we expect that to scale up. So what is our deployment strategy today looking like? So we use SageMaker single model endpoint. Both of these require 2 GPUs. So I have deployed 2 copies of my CodeGen model since it's having more traffic, and 1 copy of the TextGen model. Right? Both of these are deployed on P4Ds. Since it's a single model endpoint, I have to have 2 P4D instances. Is this kind of a deployment familiar to you guys? Have you been using this? Yeah? So as you see here, we have to use 2 P4D instances, super expensive ones, which are significantly underutilized. Right? Now think about scaling this up, not only for more traffic, but more models. It's an operational nightmare. It is very hard to do it, and you are still paying a lot because you're underutilizing the resources for these models. Right? We looked at multi-model endpoints, what Dhaval talked about. But those are good for smaller models, which are homogeneous. But for these larger foundation models, since you have to load them up in the memory, the SageMaker inference component endpoints was the right solution for us. So how did we do that? On the same instance with SageMaker inference component endpoint, we were able to deploy both the models. So in pink, you see copy 1 and copy 2 of model A, CodeGen, and in blue, you see it for the TextGen models. Now, this completely utilizes or better utilizes the P4D instances that we have and does this without any performance penalty. So we did side-by-side comparisons of how our traffic was going in for single model endpoints and now with the inference component engine. And with the smart routing functionality, we didn't see any performance penalty. So as our models scale up, how does this look like, right? So initially, with the single model endpoints, as we would scale up, we would need to now add more instances onto it. So if my traffic's tripled up, I would need to spin up another instance for the code gen model, another instance for the text gen model. So now I need 4 of them. But now if I look at it from the inference component endpoint, as my traffic scales up, I'm able to better utilize the instances, and I would need only 3 instances of P4Ds to get the same throughput, same request going through. Again, like you see, better utilization of the resources, less number of instances, hence less cost to all of us. Okay? So what are some of our learnings that we saw? So scaling using inference component endpoints requires single endpoint to manage. Super useful, especially if you go and scale up to hundreds of models that you have to practice. It is much more optimal utilization of the hardware resources. The key thing was you can independently scale each model, and then the auto-scaling functionality was very useful for managing these resources. Scale to 0, what Alan mentioned, was another useful functionality, especially in the non-production environments, in our lower test and performance environments, because what we could do is for a period of time, scale it up for running our tests, and then bring it back down as soon as this is done. This was not the case in the single model endpoints or any of the other solutions. And cost savings, as I showed you, as we scale up, and performance was also at parity. So what are some of our key takeaways? The first step you would want to do is you want to identify the foundation models which use the same hardware and host them on a single endpoint. Use inference components. It takes away a lot of your heavy lifting. It reduces your compute footprint without any performance impact. The auto-scaling functionality for us worked really well. We were able to scale up and down the model's usage based on our incoming traffic. The smart routing functionality that Alan mentioned was very useful for getting performance parity. And then for us, for the code gen models, especially the first byte latency was important. And so it's true for most of the use cases. So use response streaming. And the last one, the large model inference container, that was very useful as compared to some other containers that are there for doing inferences for foundational models. Those are some of our key takeaways. So with that, I'll call back Dhaval.
Thank you very much, Bhavish, for the awesome story. Thank you very much. So I'm going to just deep dive into some of the things that we introduced recently. 2 days ago, we launched new features into the large model inference container that I want to dive deep quickly. So what we have here in terms of hosting foundation models on SageMaker, we have large model instance container that already supported deep speed. It also supports the other model parallel approaches like Hugging Face and Accelerate. And it also has support for now, the new support for TensorRT LLM. And we also introduced additional optimization techniques for all reduce, which enables the optimal communication between the NVIDIA GPUs internally for the model parallel distributed inference. So you can, if you use all these features and functionalities, and now you can get 20% lower latency on average. Compared to the previous versions of the large model inference container. So do use large model inference container in SageMaker and for any type of the foundation model, be it a text or large language model or stable diffusion type of model or any kind of text to image or image to text type of models. We also have support for the stable diffusion backend. We also have other optimized engines like Faster Transformer that you can use to host FLAN T5 or T5 family foundation models as well. And you can use the single inference container to host this variety of foundation models at scale. You don't have to keep on using different containers for different types of models or encoder architecture or decoder architecture. This is a unified, single, large model inference container that you can standardize on and use and leverage this for cost efficiency and high performance. Now with that, Here are some references that you can use in order to boost the inference performance for foundation model and some of the new features that we launched 2 days ago in large model inference container, and then the new SageMaker inference components feature that we launched. You can find more information here. You can definitely scan code that, and you'll be redirected to the resource directly. And with that, we'll be extremely happy to get your feedback for this session. So do go to your app, select AIM327, and please provide us feedback. And with that, thank you very much, Bhavesh. Thank you, Alan, and thank you all for attending this session. Thank you very much. We'll hang out here. If you have any questions, we'll be happy to answer your questions. Thank you very much.